The Lewis dot structures of polar covalent molecules are very similar to the Lewis dot structure of covalent molecules. As a matter of fact, they're done exactly the same way. Let's look at some examples here on this slide. Start with the molecule iodine fluoride. Actually, we would call that technically iodine monofluoride. Notice, of course, these are both column 17 elements, 7 Lewis dot structures. They each need one more electron. Now, if they were far apart in the periodic table with vast differences in electronegativity, then we would have an electron gainer and an electron loser. But since they have similar electronegativities, even though fluorine is more electronegative, it still cannot pull the electron loose from the iodine, so there is a degree of sharing. Now, it's not an equal sharing. That's why we call it polar covalent. There is a little more buildup of electron density on the fluorine than there is on the iodine, but nowhere near the I plus F minus that you would see if this was an ionic compound. So, since we're going to treat this polar covalent molecule just like a covalent molecule, what we will do is have each element kick one electron into a sharing zone between the I and the F. Then the I thinks it has the electron shared to it by the F. The F thinks it has the electron shared to it by the I, and each has a complete octet. On the right, we see another example of a polar covalent molecule formed by combining bromine with chlorine. That would be bromine monochloride. Again, each is a column 17 element with 7 valence electrons. Each will kick one into the sharing zone. There will be a single bond, as the picture shows, between the bromine and the chlorine, and there will be 3 non-bonding pairs of electrons on each of those 2 elements. Then I have an example of bonding P with N in what would be known as phosphorus mononitride. These are column 15 elements with 5 valence electrons, as you see in the depiction, and each needs 3 more electrons. And again, since their electronegativities are not dramatically different, you can't have an ionic situation, so each will contribute 3 to the sharing zone for the other to use. And so we have a triple bond between the P and the N and 1 non-bonding pair on each. It is quite common to replace a pair of electrons with a single line connecting the dots, if you like, between the bonding elements. As you see here, as I show for the diatomic element F2, I have removed the bonding pair being shared between them and replaced that with a single line. Now, typically, this is only done for the bond pairs of electrons. As you note, I have left the depiction of the non-bonding pairs as dots. This is very commonly done because chemists use these dots and transfer them and move them around in a variety of electron choreographies when you start to look at the reactivity of molecules. So again, you will note I've replaced bond pairs with a straight line, sort of showing how the bond is connecting atom A to atom B. So for F2, which had a single bond of 2 dots between the F's, I put a straight line, and again, like I said, I left the lone pairs or non-bonding pairs as dots. And I show the same example below for the phosphorus mononitride molecule, where I take the 3 shared pairs of electrons, convert those into 3 lines. Now remember, we call that a triple bond, and in the line notation, it certainly shows the triple bond character much more elegantly, if you like, between the P and the N. Notice, if I'm going to count the valence electrons that each atom has, what you should do is for each line touching an atom, claim that is 2 electrons. And of course, for dots, count the dots as well. So if I look at the P, I see 3 lines 2 dots per line. That's total of 6 electrons on the p, and then I have 2 dots on the p, so that's a total of 8, or a complete octet around the p. Likewise for the n, I have 3 lines, 2 dots per line, 6 valence electrons, plus 2 non-bonding dots. That gives 8, or a complete octet around the n, as well as around the p. This slide discusses the relative energy of the various bond types that we've looked at. Now, first of all, we should recognize that chemical bonds are a rich source of what is known as potential energy. We'll have much more to say about potential energy later when we do a little bit of thermodynamics, but as a little preliminary discussion here, potential energy is the desired energy that we harvest from a variety of sources to convert into motion. This might be motion to drive our car, or it might just be kinetic motion of a whole bunch of molecules to deliver heat to some system. But in other words, as we will discuss in much greater detail later, chemical bonds store potential energy, which can be converted into energy of motion and can be used by humans. Okay, so for instance, as I also mentioned there, combustion is the process by which we release, as one process by which we release this energy stored in chemical bonds. I think it's safe to say that the original reasons behind humans getting involved in practicing chemistry was to harvest energy. There's no doubt that fire was probably the first chemical process humans concerned themselves with, and no one was really concerning themselves at that point with what the fire was actually doing. What they were doing when they were burning a fire was harvesting the energy, the light energy, the heat energy, even the protection that it provided when they burned a fire. Now, each pair of electrons in a chemical bond is a storage well, if you like, of this so-called potential energy. And the more bonds that are distributed between atoms, the more energy that is possessed in that bonding system. So quite naturally then, a triple bond is a very high energy bond, a double bond is a medium energy bond, if you like, and a single bond is a lower energy form of bonding. Now, what I mean by this is twofold. If you're going to break a diatomic molecule apart that has triple bonds, you're going to have to input a much more amount of energy to pull them apart. The attraction that's holding them together, the binding between them, the sharing of all those electrons between the two makes them much more difficult to get apart. Likewise, if you have a single bonded collection of atoms, then less energy would be required to yank them apart. Now, more so than that, also once you begin the cascade of breaking a collection of bonds for a huge set of molecules at the same time, what you will also find is that more energy is released when you rip triple bonds apart than is released and can be used in other processes if you rip double bonds apart, and there will be more in that case than will be released when you rip single bonds apart. One thing we should note at this juncture is that O2, the stuff that fuels our lives and supplies the energy not only for all animals to maintain life, but also supplies a great deal of the energy in normal combustion processes that we endeavor into when we burn fires. Remember, oxygen, O2, with its 6 valence electrons for each O, has to double bond the O's because each O kicks 2 electrons into the sharing zone. This energy-rich double bond that oxygen molecules possess is the source of a vast amount of energy that is, again, used in fires, but also a vast amount of energy that is consumed by animals in their aerobic respiration processes. Reiterating what I said on slide 3, the energy stored in bonds is released, and the energy in bonds is tied to the strength of those bonds. And as I say here, it takes more energy to break triple bonds than it does to break double bonds, but also more energy is released upon breaking triple bonds than is released upon breaking double bonds. Now let's turn to the relative length of the bonding types. Now what we can think of is the fact that a triple bond has much more electron density placed between the atoms than a double bond has placed between the bonding atoms than a single bond has placed between the bonding atoms. Now what this electron density allows is the positive charged nuclei for those bonding atoms to get closer and closer and closer together. So naturally, then, with the more electrons you put between nuclei, the less repulsion those nuclei experience, and the closer those nuclei can get together. So the higher the so-called bond order, which means the more electrons in the bond, the shorter the bond length. So the distance between connected nuclei decreases as you go from a single to a double to a triple. Or as I say there, triple bonds are less in length than double bonds, which are less in length than single bonds. Let's now discuss how we are going to do the Lewis dot structure of polyatomics other than diatomics. Now I'm sure you've seen chemical formulas such as those we're showing on this slide, the top one being nitrogen trifluoride. The convention in chemistry is that you surround a lone atom with a subscripted set of atoms, and the connotation is that the subscripted multiple atoms are connected individually to the lone atom. So when I have NF3, what you do is you put N in the center, the lone atom in the center, and the three F's are connected around to the N. So now what we can do is think about the Lewis dot structures of how that would play out. N is the central atom in NF3. N is a column 15 element with 5 valence electrons. And this is very convenient, and you can see why it would be natural for NF3 to form. Why? Because if the N gets 1 electron from each of 3 F's, it will complete its octet. Likewise, this is why the F's connect singly to the N individually and don't connect in a line, N, F, 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 something like that, because F is a column 17 element, which is a, as you can see here, 7 Lewis dot structure for F. F's each need 1 more electron, and even though F is more electronegative than N, it's not that much more electronegative that it can yank the electron loose to make an ionic bond. So F does have to share electrons with N. Now, let's get it straight though. F is more electronegative and doesn't share equally, so the bond is what we call polar covalent. The name implying it's covalent, meaning share, but it's polar covalent, meaning the F is a little more negative than the N in this sharing of electrons. So you place the N in the middle, you let the N share 3 individual electrons outward to each F, you let the F share 3 individual electrons inward to the N, you form 3 single bonds between the N's and the F's. In the top picture I show this with dots, in the bottom picture I show it with lines. Now, which way you would prefer to do it when you show them to me would be up to you. Probably, though, in the new arena in which we're going to be presenting these, I don't see any possibility other than me showing you the pictures and you deciding which way the connections would be correct. Okay, so that still doesn't preclude you from understanding the ability of how to connect an N to three Fs, because what if, as we've seen in upcoming possibilities, the central atom does multiple bonding outward to the external atoms. You certainly have to be able to distinguish that for yourself. Then let's look at the bottom example I show for a polyatomic molecule, and that would be carbon dioxide. Now again, the idea is you put the carbon in the middle, you connect O's not consecutively to each other, but you connect one O to one side of the carbon and one O to the other. The next over picture shows the valence electron structure of both carbon and oxygen. Oxygen, column 16, 6 valence electrons. Each oxygen needs 2 more. And since the oxygens are connected directly to carbon, not to each other, the only place oxygen can get 2 more electrons is from carbon. So carbon, you can tell right away, will be kicking 2 electrons into the sharing zone. Now, let's turn to carbon. Carbon is in column 14. It's a 4-dot Lewis dot structure. Carbons need 4 more dots to complete their octet. And since they're connecting to 2 O's, the idea would be is that each O gives 2 dots inward to the carbon as the carbon gives 2 dots outward to the O. Now to the right of the O and C atomic Lewis dot structures, I show what it would be like if carbon and oxygen single bonded. If you count the shared pairs of electrons between the C's and O's, the O's have complete octets if there is single bonds between C and O. The C, on the other hand, is not getting any return electrons from the O in the way I've drawn it there. So the C is still short 4 valence electrons in its attempt to complete its octet. The only way you can draw this so that both the central C and the external O's have complete octets of electrons is if the C gives 2 electrons outward to each O, while the O on the outside each gives 2 electrons inward, to the central C. And so the picture you should take for the correct way to bond CO2 is the picture I show on the far right of the page, where I have in either dots, 2 pairs of dots connecting O to C, and you can think of it as the O puts 2 into that sharing zone, the C puts 2 in, and 2 put in for the right C as well, and the C giving the right C 2 dots outward. Now notice then, when this is completed, the central carbon has no non-bonding pairs of electrons left. All of its electrons are involved in bonding. The oxygens on the outside each have 2 non-bonding pairs of electrons, and if you were to draw these pictures for me, I wouldn't care where the non-bonding pairs are placed, on the top and bottom, or maybe one on the side and one on the bottom. I do prefer that you do leave them in pairs, because that's how they exist in their non-bonding form. They exist in a spin up and spin down state so that they can get close to each other, as we talked about is the case for atoms. Now notice in the bottom picture of CO2 correctly put together, I show the bond pairs each replaced by a single line. So there is a double bond from the C to the O in each case, and that represents 4 valence electrons shared between C and O. Now one more thing we should keep in mind that you should make sure you make this connection when you're trying to decide which is the correct Lewis dot structure. First, each atom has to have a complete octet. The CO-CO single bond formed does not have complete octets of electrons around C. The C double bond O picture does have 8 shared pairs of electrons around both O and C. The next thing you have to make sure that you take into account is, does the carbon and oxygen total number of electrons in the molecule, valence electrons in the molecule, are the total valence electrons properly represented? 2 O's, each having 6 valence electrons, mean there should be 12 dots from the O's. 1 C with 4 valence electrons, meaning there should be 4 dots from the C. So there should be a total of 4 plus 12, or 16 valence electrons in a correct Lewis dot structure. If you look at the double bond Lewis dot structures and count lines as 2 dots and dots as dots, you see 2, 4, 6, 8, 10, 12, 14, 16 valence electrons represented in the pictures, as there should be. Let's do that same thing in the upper picture for NF3. There are 3 times 7, or 21 valence electrons due to the F, and 1 times 5, or 5 valence electrons due to the N. That gives 26 total valence electrons that should be drawn when you draw the NF3 molecule. If you turn then to the correct Lewis dot structure, count the Lewis dots you see in the picture, you will find 26 Lewis dots in that picture. Let's look at the interesting case of the Lewis dot structure of carbon monoxide. Of course, this means a situation where we bond a C to a single O. C has 4 valence electrons, O has 6 valence electrons. One thing you take from that is that when we are done, the finished molecule had better have 10 valence electrons. So let's then think how we can complete this by sharing electrons between C and O. Well, oxygen needs 2 more electrons. It's not pulling them out of thin air. The only place it's going to get them is from C. So immediately you know C is putting 2 valence electrons into the sharing zone. Carbon, on the other hand, needs 4 more electrons. The only place it can possibly get them is from O. So immediately you imply oxygen must put 4 electrons into the sharing zone. To do so then, what we're saying is we make a triple bond between the carbon and the oxygen. And notice the similarity to the bonding of carbon monoxide to the bonding of N2. Think about N2, a column 15 element, 5 valence electrons on each N, a total of 10 valence electrons. So now when I do CO, carbon kicking in 4, oxygen kicking in 6, 10 valence electrons need to be used to connect C to O. In both cases of N2 and CO, 10 valence electrons total are used to connect the 2 atoms together. It should not be surprising to you then that the way in which CO bonds is exactly the same as the way in which N2 bonds. They are, in fact, isovalent. Now, as a matter of fact, if I were to make the polar covalent molecule boron monofluoride, B is a column 13 element with 3 valence electrons. F is a column 17 element with 7 valence electrons. B needs to share electrons correctly. B would need to gain 5 more electrons, so the F would kick in 5 electrons. F needs 1 electron, F would kick in 1 electron. There would be a total of 6 electrons shared between the two. There would be a triple bond between the B and the F, and because there are, again, a total of 10 valence electrons between the B and the F, so they must be shared in that fashion. Now let's look at the case of sulfur trioxide, SO3. Now, first of all, I want to point out to you very importantly that some of you might say, hey, wait a minute, that's sulfite. My answer to you is no. You should not recognize SO3 neutral as sulfite. Of course, those of you who by now have committed to memory your polyatomic anions, which I require that you know, recognize that sulfite is SO3 minus 3. And I want you to make that distinction. SO3 minus 3, yes, you will give it a nomenclature of sulfite. SO3 neutral is not a polyatomic ion, it is a molecule. And we call molecules by the name, as the convention we talked about on this previous set of slides, we use the name sulfur trioxide to represent that connection. Okay, so now let's think about how we're going to put SO3 together. SO3 means S is in the middle, 3 O's individually connected to S. So I need to decide how many electrons S needs, and I need to decide how many electrons the O's need, and then have them shared outward from S to O. So S and O are both column 16 elements. Column 16 elements all have 6 valence electrons. So each of these has a 6-dot Lewis dot structure. Now, quite simply, let's fix the O first, because it's easy. O each need 2 electrons. Very conveniently, S has 6 valence electrons. So each O will receive 2 of S's 6 valence electrons. So you send 2 electrons out to each O from the S. Now, if you do that alone, as I did in the structure on the left, yes, the O's are now satisfied with complete octets, but the S cannot just share outward to O. Why? S isn't being satisfied in that case. S demands, because it's got 6 valence electrons, that somewhere it gets 2. It is getting them from O, but you cannot have 2 of the O's each kick 1 into S. That doesn't work. Why not? Because electrons must maintain pairing in order to be spin up and spin down so that their repulsions are minimized. So what happens in convention is that since S needs 2 more electrons, one of the O's decides it will be the nice guy and put a pair of electrons into the S. So only one of the O's contributes to S, and that one O contributes a pair of spin up and spin down electrons inward. So you'll notice on the right picture what I show is S is giving 2 upward to the top O, 2 to the left O, 2 to the right O, but the right O is also kicking back 2 electrons to the central S. So there is one double bond between S and O and 2 single bonded S2O atoms. Notice all total electrons are accounted for in this picture. Remember, there should be a total of 6 times 4, yes, that's correct, 6 times 4, or 24 valence electrons in the proper Lewis dot picture. The SO3 I show on the right, and actually the one on the left, as a matter of fact, does too, the SO4 on the right and left both have 24 valence electrons. Count them up if you don't believe me. Now, the reason that the right Lewis dot structure is correct compared to the left is the fact that the complete octet is also satisfied for all atoms. As long as the electrons are in the sharing zone, we can count them for either atom they are pointing towards. The left-hand SO3 picture does not demonstrate a complete octet for sulfur. Only the right Lewis dot picture represents a complete octet for sulfur. So in conclusion, one of the O's double bonds, and the S gives two pairs of electrons outward to each O, and so everybody gets a complete octet. Now, you'll notice that I define on this slide also the term resonance. Resonance is the equal likelihood of which O happens to be double bonding. You'll notice in my picture I arbitrarily chose the right O to double bond to the S. Who's to say that the left O doesn't double bond to the S? Who's to say that the top O doesn't double bond to the S? As a matter of fact, nature is quite fair. What happens in nature is that this double bond literally hops around from the left O to the top O to the right O, to the left O to the top O to the right O, meaning each O has a turn kicking in the two electrons individually. Now, what empirical or experimental evidence do we have to show that there is not a single individual double bond, but also what really is going on is there are three simultaneous double bonds that are each individually happening at a time? Well, here is the evidence that I can cite for the fact that we know this is true. We know this is true because if it was true that one bond was double and the other two were single, that would mean, according to our previous discussion, that one of the bonds would be stronger than the others, meaning it would take more energy to break one of them, and the other two would take less energy to break. The other thing that one double bond and two singles would imply would be that one of the bonds would be shorter than the others, because double bonds are shorter than single bonds. According to the experimental evidence that we have found over the years, all the bonds in SO3 have exactly the same length. All the bonds in SO3 have exactly the same strength. So it turns out that the length of those bonds is not quite as short as a true SO double bond turns out to be, and the length of those bonds is not as long as an SO single bond tends to be. It's somewhere between. So the best idea we can come up with is to allow for the double bond to hop from the S on the left to the S on the top to the S on the right. Now, what we will call that is a resonance structure. This shows how the double bond can be simultaneously distributed between any of the three outward oxygens to the central sulfur. So what I am showing on this slide is the Lewis dot structure of the three so-called resonance structures of sulfur trioxide. The top complete dot picture is the one that I showed correctly built from the previous slide. So now what I'm showing below that using lines instead of dots, remember for a double bond you use two lines, for a single bond you use one line. I've replaced all bond pairs with lines to show the way the double bond can be moved from the right O on the left picture to the left O in the middle picture to the top O in the right-hand picture of the resonance structures of sulfur trioxide. I want you to be able to recognize this concept. It's a very important concept that you will use over and over again in organic chemistry. The implication again is that all these bonds are technically the same. They're the same strength and length. So what we're trying to demonstrate by this resonance picture is this double bond hopping around from position to position. Again, remember, there also should be 24 electrons in this 6 times 4 valence electron set. And if you count any of those 3 central Lewis dot structure pictures, you will count 24 electrons represented by lines and dots. Also, all atoms should have a complete octet, and if you count the, again, lines as 2 dots, and how many lines are touching each atom, plus their non-bonding pairs or dots that they have connected to them as well, each atom in the resonance pictures has a complete octet of around it as well. So please again note, and we'll see some examples further down the road of resonance structures that can be drawn in particular bonding cases. On this slide, I again discuss the concepts behind our experimental evidence, which indicates to us that atoms of this, or bonding atoms of this type, must exhibit resonance structures among their Lewis dot forms. It again is because of the fact that SO double bonds should be shorter and stronger than SO single bonds, and there is no experimental evidence that any of the bonds in sulfur trioxide is shorter, or that any of the bonds in sulfur trioxide is harder to break. They all, as a matter of fact, have exactly the same length, and these lengths are somewhere intermediate between what a typical sulfur-oxygen single bond and a sulfur-oxygen double bond are, and the energy to break them is also intermediate to the amount of energy it typically takes to break a true sulfur-oxygen single or double bond. Let's now turn to how we represent the Lewis dot structure of polyatomic anions. For instance, here I show phosphate, which of course is PO4 with a total charge of -3. Now, where does the phosphate get the 3 electrons it needs to be built? It gets them from calcium, magnesium, iron, some other ionic material, a metal which donates electrons to the phosphate. So, here's how we are going to do the representation for phosphate. The central atom P is where I will place the 3 incoming electrons. Remember, phosphate has an additional 3 electrons above the neutral collection. So what I did in this picture that I'm showing you here is depicting those 3 electrons that were gained from the outside side. Instead of with red circles, I'm representing them with E's. So on the central P, which is a 5-dot Lewis dot valence electron structure, because it's in column 15, I placed 3 extra electrons from the charge that the polyatomic anion gains. Notice that conveniently that completes the octet of the P. But now the 4 O's attached, each column 16 elements, each needs 2 more electrons. So conveniently, you slide each O onto a pair of electrons from the central P. So the top O slides on, the 6 valence electrons slide onto that 4th set. The bottom one, the left one, the right one, I just slide them all on, and voila. Each element has a completed octet as a result of doing that. Now, another thing I want you to see that we are doing as we draw these Lewis dot structures. We put the entire polyatomic anion in brackets, and we put the total charge on the polyatomic anion outside the brackets. Here's what the connotation of that means. I'm stating that some metal donated 3 electrons to this system. I claimed as I built it that those 3 electrons were distinctly and definitively put on the central atom. The idea with the brackets is saying that those 3 electrons could be anywhere spread over this molecule. They could be on the top O, the left O, the bottom O, the right O on the outside. They don't have to be in the bonding region between the P and the O. So that bracket notation with the charge on the outside is generally an indication that somewhere, somehow, 3 of these electrons have come from an external source. So when you properly draw a Lewis dot structure, it should always have a bracket around it and the total charge on the outside. Whether or not you use E to represent the dots that have been gained, I don't really care. I'm just doing it here for demonstrative purposes. The next thing we should keep in mind is that every atom should demonstrate a complete octet, which they do, and the total number of valence electrons represented in the picture should be the total number of valence electrons available in PO4 minus 3. Remember, P is a 5-dot structure plus 3 given to it from the external metal. That's a total of 8 for that. Then there are 4 O's with 6 each. That's 24. So there should be 32 total dots represented in PO4 minus 3. If you count the dots that you see in the picture, you will find it comes to 34. Now let's contrast with the way in which we will do the Lewis dot structure of a polyatomic cation. Here I'm using ammonium, NH4 plus 1. Now, the idea here is somehow to build ammonium, you must shed an electron. Where does that electron go? It gets donated to a nonmetal, making something such as ammonium chloride. Well, in any event, what you do is that the central N is where the electron is removed. So a neutral N would have 5 valence electrons. The N in ammonium, since ammonium is a +1 cation, has 1 valence electron removed. So what I do is I have a remainder of 4 valence electrons on the central N. Then I let each N share an electron outward to an H. Remember, H's do not want a complete octet. H's are trying to complete the electron requirements of row 1. The requirement of row 1 is to only complete the 1s orbital with 2 electrons. So instead of having a complete octet, we can say hydrogen is looking for a complete doublet of electrons. So 2 electrons satisfy the energy electron requirements of H as opposed to 8 for, say, a row 2 element like N. So my N has 4 valence electrons remaining. After it gives up 1 electron, it sends each of those 4 electrons outward to a single H, while each H kicks 1 electron into the N. The N in the middle then has a complete octet of 8 electrons around it, while the H's have a complete duet, if you like, of 2 electrons. So notice again, N plus 1 means 4, plus 4 from hydrogen 8. There's a total of 8 electrons for the valence level of NH4 plus. Once again, the other thing that you do, as we do for all polyatomic ions, you surround the polyatomic ions Lewis dot structure with brackets, and you put the total charge on the outside, indicating that electron didn't necessarily have to be removed from the central N. It could have been removed from anywhere in the structure. Let's look at the Lewis dot structure of the possible anions that are built from chlorine. Let's begin with, on the top left, with chloride. Chloride, of course, is Cl-1. Chlorine is, of course, a column 17 element, 7 valence electrons, so chloride naturally has a completed octet from the 1 electron it has gained. Now remember, where did that electron come from? Probably from some metal which was dying to get rid of an electron. Let's now extend this to the hypochlorite anion. Remember, this is one of the ones that I expect that you would know. It is ClO, and it is always -1. And it can connect to form sodium hypochlorite, potassium hypochlorite, and on it goes. Well, again, there is a need for 1 extra electron. I'm just going to put that in the same position I put it on in chloride. So I'll just put an extra electron onto the chlorine, which completes its octet. Then I slide a 6-valent electron O onto one of those 2 electrons on the chloride. So I make a ClO single bond from 2 outwardly shared electrons from the Cl, leaving 6 non-bonding electrons remaining on that O. Remember, ClO -1 should have 7 + 1 + 6. That's 14 total electrons to build it, and you will note that the hypochlorite anion has 14 valence electrons represented in that Lewis dot structure. Each atom also is showing a complete octet. Let's move to the chlorite anion, which of course is ClO2 -1. Once again, I'm going to treat it like I have chloride in the center with a 7 valence electron neutral chlorine gaining an electron to make a complete octet. Then I'm just going to slide 2 O's onto those 8 valence electrons around the chloride. And I'll slide 1 on the left and 1 on the right, making single bonds outward with 2 of the lone pairs of electrons that originally were on chloride. And again, to indicate I'm not sure where that extra electron came from, I should put the entire polyatomic anion in brackets and the charge on the outside. Now I can move to the chlorate anion. Remember, the ATE ending is the most common form of the polyatomic anion, as we talked about in our nomenclature discussions. I'm just going to continue this idea. I'm going to slide a third O onto one of the non-bonding central pairs of electrons on the chloride, and you can see that makes the structure of chlorate very nice. And then finally, the perchlorate ClO4 -1 slides a 4th electron onto the remaining pair of electrons on the central chlorine. Let's do the same thing for the polyatomic anions that can be constructed using nitrogen. First, let's begin with nitride. Remember, nitrogen, column 15 element, 5 valence electrons. Nitride is completing the octet by becoming N-3. Now then what we can do is make the so-called hyponitrite anion, which is NO-1. NO-1 is a structure that will have a total number of valence electrons of 6 plus 6 or 12 valence electrons. So again, that's 6 plus 6 or 12 valence electrons required to build a so-called hyponitrite. Now, again, let's think back to other structures we have encountered previously that have 6 plus 6 or 12 valence electrons. The first one that comes immediately to mind is O2. O2 is formed by two 6-valent neutral atoms. So there's a total of 12 valence electrons to build O2. It takes a double bond between the O's to make O2. Just like it takes a double bond between the N and the O to make hyponitrite. So, in other words, the N on the left is taking the place of an O, but it is now an N that has an extra electron added to it so that it is isovalent to O. So, notice in my picture then, each N and O in hyponitrite has a complete octet. Each N and O has, or the total number of electrons in the N and O is 12. Count up the dots and the lines, plus the 1 valence electron that was thrown into the mix. I get a total of 12 valence electrons for that hyponitrite. Now let's turn to the nitrite anion, which is NO2 minus 1. Okay, so again, NO2 minus 1, I need an extra electron to be put into the mix. I will put it onto the central atom, N. Now the N, of course, again, then will have 6 electrons to work with. The N in the middle needs 2 more electrons. It has to get them from the O's that are connecting to it. Once again, we will never have a single contributed electron from one O and a single contributed electron from another O. The N in the middle needs a pair of electrons, and it gets a pair of electrons from one of the O's. One and only one of the O's. So what we're going to see, also note, is that the outer the outer O's each are short 2 valence electrons. So N will give 2 valence electrons out to the O on the left and out to the O on the right. What this results in is that the N will single bond to O on the left and double bond to O on the right. Now the other thing you should note is that you can draw resonance structures for the nitrite anion. The one I'm showing you has a single bond left, double bond right. Why wouldn't nature allow there to be double bond left, single bond right? And this would be an equivalent structure for nitrite. So there are 2 resonance structures of the nitrite anion as I allow the single and double bond to hop between the N and the O. Okay, now let's turn to nitrate at the bottom. Nitrate is NO3 minus 1. Now the first thing I want to point out to you is that NO3 minus 1 is isovalent to SO3 neutral. It is isovalent to sulfur trioxide. Now what that means is, since it has the same number of valence electrons as sulfur trioxide, it should have the same kind of bonding as sulfur trioxide. Sulfur trioxide example was done about 3 slides back. And what we learned from doing it was that the outer O's each needed a pair of electrons, so the central atom kicks 2 out to each O, but the central atom, whether it's N minus 1 in this case or S in the sulfur trioxide case, the central atom is still short 2 electrons. So one and only one of the O's can kick 2 in as the N kicks 2 out to each O. So we will form a double bond to one of the O's and a single bond to the other 2 O's when we form nitrate, just like we formed a double bond to one of the O's and a single bond to 2 of the O's when we formed SO3 neutral. Again, it is isovalent. There's isovalence between NO3 minus 1 and SO3 neutral. so the bonding scheme has to be exactly the same in both cases. Finally, we should note that there would be a there'd be 3 resonance structures possible for the nitrate anion. I'm showing the one where the O is double bonded to the top N to the top double bond O. It could also be N to the left double bond O or N to the right double bond O equally well. So there are 3 resonance structures of the nitrate anion. Finally, I talk about the pernitrate anion, which is a little bit weird. Usually these names go along with the same oxidation number. In this pernitrate anion case I'm showing, the central nitrogen gains 3 electrons, and so that completes the octet on the central nitrogen, leaving 8 electrons around it. And then, since each O in the NO4 needs 2 more electrons, a pair of electrons from the central N goes outward to each outer O. And again, to keep with the total picture, I draw a bracket around the whole thing and put the total charge on the outside, as I've talked about. Now remember, on this pernitrate as well, there should be a total of 5 plus 3 plus 4 times 6. So that's 24, 29, 32 total valence electrons in the Lewis dot picture. If you count up the lines and dots in the pernitrate, you will find 32 electrons. Finally, let's talk a little bit about formal charges. Formal charges are a bookkeeping scheme that chemists use to keep track of how many electrons are distributed on atoms in a molecule. Typically what we do with the formal charge is we try to keep all the atoms happy by not having them have a total wacky amount of charge by the amount of electrons it is sharing or gaining when you put the compounds or molecules together. So formal charge is useful to determine the relative stability based on if the charge is evenly distributed over the atoms. It tends in nature to be more favorable as to whether or not that particular way of connecting the atoms is more likely to occur in nature. How do we define the formal charge? Well, the formal charge on the atom, as we see there, is equal to the number of valence electrons it should normally have minus the number of valence electrons it has in the bonded case. And how you can do that, as the bottom thing shows, this is the recipe you should keep in mind. Formal charge on an atom is the number of valence electrons on the free atom minus half the number it is sharing in bonds minus all of the electrons it is not bonding. So for all dots represented by lone pairs, you subtract that off. For half the electrons in bond pairs, you subtract that off, and you subtract that from what number of valence electrons you start with. So maybe it would be better if we just show this on some examples in some upcoming slides. Let's begin with the formal charge on carbon monoxide. First of all, carbon monoxide is a C bonded to an O. C with 4 valence electrons, O with 6, 10 total valence electrons to distribute between them. Carbon needs 4 more, it's only getting them from O, so oxygen kicks 4 into the share. Oxygen needs 2 more because it started with 6 valence electrons. Oxygen needs 2 from carbon in the share, so carbon has 2 electrons remaining in a non-bond pair. After oxygen puts 4 in, it has 2 remaining in a non-bond pair. So carbon monoxide is triple bonded between the C and the O, and again, that's isovalent to N2. Now, How then do we do the recipe to calculate the formal charge on each atom? Start with the total number of valence electrons it begins with, which is 4. Then subtract half of the bonding electrons. There's a total of 6 bonding electrons on carbon. So half of those that it gets to think that are its are 3. So we'll take 4 minus 3, and then subtract all non-bonding electrons. There's a single lone pair on C, so I'll subtract 2. So I get 4 minus 3 minus 2. The formal charge on the carbon in carbon monoxide is -1. Now let's go to the oxygen. The number of valence electrons is 6. Half the bonding electrons, there's 6 total bonding electrons, so I'll subtract 3. And then it has a lone pair, so that's 2 non-bonding electrons. I'll subtract 2 more. 6 minus 3 minus 2. The formal charge on O in CO is +1. Now notice that the total formal charge on all atoms is +1 and -1. It's 0. That adds up to the total charge on the molecule itself. Carbon monoxide is neutral, so the sum of all formal charges on all atoms has to be neutral, just like we see here. Now let's look at the case of ammonium. Ammonium has 4 hydrogens that are all exactly the same. Each of them has 1 valence electron, and it gets half the bonding electrons, which is 1. It has no non-bonding electrons. The formal charge on H, each of the H's, is 0. Now let's do the formal charge on the nitrogen. It begins with 5 valence electrons. Take off half the bonding electrons. That's 1 from each bond, or 4. That has no non-bonding electrons on it. So I take 5 minus 4. I get +1. So each hydrogen has a formal charge of 0. The nitrogen has a formal charge of +1. That's a total sum of formal charge of 0 plus 0 plus 0 plus 0 plus 1. That's a formal charge total of +1, as it should add up to the charge on the molecule. Let's next look at this molecule. I show hydrogen cyanide on the left here. This would be the Lewis dot structure of hydrogen cyanide. Let's do the formal charge on H, and we can do it here. I just wrote them out, but let's think about it a little bit. The number of valence electrons on H is 1. There is half the bonding electrons is 1. There are no non-bonding electrons, so I should do 1 minus 0, or a 0 formal charge on the H in HCN. How about the formal charge on the C? It begins with 4 valence electrons. I subtract 1/2 of the bonding electrons. It has 8 total bonding electrons with the 4 lines touching it. It gets half of those, so you subtract off 4 for the bonding electrons. It has no lone pairs, so I would do 4 minus 0, 0 formal charge on the carbon. Now I'll turn to the nitrogen. It begins with 5 valence electrons. Half the bonding electrons is 3, so I'll take 5 minus 3, and then I'll take also -2 for the non-bonding electrons. 5 minus 3 minus 2 is 0 for the formal charge on the nitrogen. This slide shows how we do the formal charge in resonance structures. Now, in all honesty, let me tell those of you that are still with me here, I am not going to ask you to do anything like this on the test. I'm showing this because this is something you do all the time in organic chemistry. These are 2 resonance structures of the way you can connect carbons to nitrogens in organic, carbon, nitrogen, oxygens, and hydrogens, as a matter of fact, in organic molecules. These both have the same number of electrons in them. You can count up all the dots and lines. 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons are represented in both the picture on the top and the picture on the bottom. Now, how organic chemists typically go about distinguishing between the Lewis dot structures which resonance structure would be possible. What they do is they count, or they look at the formal charges and see which is more reasonable. So let's get this clear. I would not expect you to be able to draw the two resonance structures that you see here. However, you should be able to figure out, based on if you were given the Lewis dot structures, you should be able to figure out the formal charge on any of the particular atoms. Let's take the top O. There's 6 valence electrons to start, minus 2 for the bond, half the bonding electrons, minus 4 for the non-bonding. The formal charge on the top O is 0. Let's now turn to the formal charge on the nitrogen. There's 5 valence electrons to begin, minus half the bonding electrons, and the wedge bonds are just meaning that there's single bonds from the end of the H. So there's 3 of the bond electrons. There's a total of 6 bond electrons touching the N. So it gets 3 of those to think it's its own. And there's a non-bonding pair. So it's 5 minus 3 minus 2, or a formal charge of 0 on the top N. Now let's go to the bottom resonance structure. It's the same molecule, bonded in a different way, now let's determine the formal charges on them. I get, when I do the O, 6 minus 1 minus 6, or a minus 1 formal charge on the O. For the N, I get 5 minus 4 minus 0, or a plus 1 formal charge on the N. So the O has a formal charge of minus 1, the N has a formal charge of plus 1. Now, how an organic chemist would try to rationalize that is, N is less electronegative than O, so if any of these is going to be more negative than the other, it's more likely that the O would be more negative than the N. So since the charge is evenly balanced in the top Lewis dot structure, and it has a weird imbalance in the bottom, organic chemists would say that the top structure is the more likely way in which these atoms would bond together to form that molecule. This slide is showing us more fun with Lewis dot structures of polar covalent molecules. Let's talk a little bit about nitrous oxide. Now that is N2O. It's commonly called laughing gas, and it has two N's, and an O. That's 10 plus 6, or 16 valence electrons, which is exactly the same as the 16 valence electrons in CO2. So the likely way in which we can connect them is either an O in the middle with double bonds outward to the two N's, or an N in the middle with double bond outward to one N and one O. So what you can then do is, if you were, again now, if I gave you these Lewis dot structures, could you tell the formal charge on each? Well, let's look at the left, NON, with O double bonded outward to two N's. Let's start with the left N. There are 5 valence electrons total, minus 2 for the bonding electrons. That's half the total bonding. Oh, I'm sorry. Wrong. There's 2, 4, 6, 8 total bonding electrons. Excuse me. Scratch that. I was right the first time. There's a double bond between the N and the O. That's 4 electrons bonding N to O. That N gets half those electrons. That's 2. Excuse me. Sorry. So again, 5 valence electrons minus 2 of the bonding electrons minus 4 non-bonding electrons. That's a minus 1 formal charge on N. The central O has 6 valence electrons minus half the bonding electrons. 6 minus 4 has formal charge plus 2. The right N, again, 5 valence electrons minus half the bonding electrons, which is 2, minus 4 non-bonding electrons. The right O has formal charge minus 1. So I have a minus 1 plus 2 minus 1, summing to 0 total formal charge. But again, they're wacky values. a chemist would say, oxygen doesn't want to be a +2. If anything, it's more electronegative. It's more likely to be negative than it is to be +2 when you put those things together. Now, if I, on the other hand, look at the formal charges on the N and O arrangement, on the left N, again, 5 minus 2 minus 4, a -1 formal charge on the N. The central N, 5 minus 4, or a +1 formal charge on that N. And on the right O, 6 minus 2 minus 4, or 0 formal charge on the O on the right. So what I learned from all that is that, again, they sum up to 0, but they're just not as wacky as you see for the formal charges on the left. So typically what a chemist would do is claim, because the electrons are more balanced, it's more likely that the bonding arrangement would be as you see on the right compared to what you see on the left. One more time, let's review that idea about the sum of formal charges. Remember, it should equal the total charge on the molecule. So if, as I would plan to do on the test, I give you a Lewis dot structure with all electrons included, you can determine the formal charge based on the picture you see in front of you, using the rules. If you see the B double bond to Cl, double bond to O, as I show, you should be able to determine that the formal charge on B has 3 valence electrons minus 2 of half the bonding electrons minus 4 for all non-bonding electrons. The formal charge on B would be minus 3. For the chlorine in the middle, begin with 7 valence electrons minus 4 for the half the bonding electrons. That would be 3 of a formal charge for Cl. And finally for the O, 6 to start with minus 2 for half the bonding, minus 4, that's 0 formal charge for the oxygen. Now if I sum the formal charges of all, minus 3 plus 0 gives a total formal charge of 0. Let's turn to the bottom case of phosphorus silicide with the triple bond between the phosphorus and silicon. Again, this is a -1 anion. If I drew this picture for you, can you find the formal charges? So I would go to the left P first, 5 valence electrons minus half the bonding electrons, which is 3, minus the 2 non-bonding electrons. 5 minus 3 minus 2 is 0 formal charge on P. Silicon begins with 4 valence electrons minus half the bonding electrons, which is a minus 3, minus 2 for the non-bonding electrons. That's 4 minus 3 minus 2. That's minus 1 for the silicon. Add up all the formal charges. You get a total formal charge of minus 1, which matches the total charge on the molecule. On slide number 20 here, I'm just showing you more formal charge examples with their Lewis dot structures. This one gets kind of complex, and I think given the circumstances, I'm not going to ask you to be able to do anything, replicate anything like this. Let me reiterate. I will give you a Lewis dot structure completed, and I expect you to be able to just tell me what formal charge there are on each atom in the completed Lewis dot structure. I won't ask you to draw the Lewis dot structures as I am doing here first, then find the formal charges. Again, on this slide, I'm showing you if you draw all possible Lewis dot structures for the combination of a C with an N with an O, you can then use the formal charges to guess which of the possible arrangements of those valence electrons would be the most likely. C would combine with N, combine with O when making a polyatomic molecule that is polar covalent. Again, I will not expect you to be able to draw all the Lewis dot structures like you see I am doing here. However, if I gave you those Lewis dot structures, which I won't give you this many, but if I were to give you any of these Lewis dot structures, you should be able to determine those formal charges that you see below them in blue. So you should make sure that you can find those, not so much find the Lewis dot structures themselves, but the formal charges, yes. You should be able to come to the conclusions of the formal charges I'm showing below each of those Lewis dot structures that are possible when C combines with N and combines with O. Same thing on this slide. I'm now showing how C can combine with N and combine with O. I'm not so much concerned that you can draw all these Lewis dot structures that I'm showing, but I would recommend that for a few of them, till you're comfortable, make sure you practice the Lewis dot structures. Not the Lewis dot structures, sorry, the formal charge calculations given the Lewis dot structures, and just to see if you can determine them. There will certainly be an example or two of that on our assessment. Let's say a little bit about the particularly important bonding schemes that carbon takes, particularly when carbon forms covalent bonds of carbon to carbon. Carbon is the most prolifically covalent bonding material in our known universe. It bonds very efficiently to itself in a wide variety of ways. Let's remember, first of all, carbon begins, since it's a column 14 element with 4 valence electrons. So carbon needs 4 more to complete its octet. So if carbon decides to singly bond to itself, it has 3 remaining attachment points. And if it would combine with hydrogens, it would just single bond to hydrogens at that point. But it could also combine with nitrogens or oxygens, sulfurs, a wide variety of other things as well. But not only does carbon like to single bond to itself, carbon also likes to double bond to itself. Now, when carbon double bonds to itself, that means it is kicking 2 electrons from each carbon into the sharing zone. So each carbon has 2 remaining non-bonding electrons that need to complete its octet. Remember, carbon still needs 8 valence electrons to complete its octet. So these remaining attachment points are seeking electrons to bond carbon in polar covalent bonds in order to complete the octet of those Cs. Now, if each carbon decides to kick 3 electrons into a sharing zone, as it often does, carbon can triple bond to itself. And that would leave 1 remaining valence electron behind for attachment. Remember, again, carbon needs a complete octet. So when triply bonding, each carbon is seeking 1 more electron from some external source. Here we show some examples of carbon either singly, doubly, or triply bonding to itself and hydrogens. We call these hydrocarbon molecules, where we connect the C's together in the chain and then attach hydrogens to all remaining points to complete octets. Remember, each line represents a bonding pair of electrons. Excuse me, one of the things you should notice about carbon, it has an aversion to non-bonding pairs. All electrons on carbons are involved in bonding pairs. So if you have a single carbon molecule, the simplest of them, as we named in our nomenclature, is methane, where carbon gives 4 single bonds outward to hydrogens. Now, if I go in the carbon naming scheme to the next possible carbon molecule. It'd be a 2-carbon chain molecule, which we call ethane. The empirical formula of ethane, as you see below it, is C2H6, but organic chemists also often write it CH3, which shows how the carbon individual methyl units are connecting to one another. You can think of it as popping an H loose and off of 2 methanes and sliding them together to form ethane. So I have a CH3 unit bonded to a CH3 unit making ethane. If I continue to propane, which is a 3-carbon, as you see as the empirical form is C3H8, but it is often written by organic chemists CH3, CH2, CH3, because it shows in that arrangement how to connect each CH unit together. I take an NCH3 unit, slide it onto a CH2 unit, slide it onto a CH3 unit, and then I have propane. Notice no non-bonding pairs of electrons, which are this is a very common feature, certainly of hydrocarbon molecules. Each carbon has a complete octet of electrons attached to it. Each hydrogen only wants 2 electrons because it's a row 1 element. Now let's look in the center at some doubly bonded hydrocarbons. I show ethene, which is C2H4 in its empirical formula, or CH2 connected to CH2. Now let's compare that to ethane. There's some madness to the method of the name. Eth means 2 carbons, ane means single bond them, ene means double bond them. So ethane and ethene are similar, except for the fact that you replace a single bond in ethane with a double bond in ethene. Now often what this is called, when you maximize the hydrogens, that's called a saturated hydrocarbon. When you have a minimum of hydrogens, we call that an unsaturated hydrocarbon. You might have heard nutritionists speak about saturated and unsaturated fats. The only difference between them is the number of hydrogens, or whether or not there's multiple bonds or there's single bonds. A saturated fat is a fat containing all single bonded carbons. An unsaturated fat, or a polyunsaturated fat, is when the molecule has double bonds dispersed in amongst the single bonds. So if I went to butadiene, the but prefix is telling me the number of carbons in the chain, and notice there begins to become again some nomenclature things we're showing here that we're not really going to overly emphasize on the test. This will be something emphasized in organic chemistry, but but means 4, 1,3 means the location of the double bonds, and diene means there are 2 double bonds distributed in the connection. Now, then at the bottom I show triple bonds. Notice, again, there's a hierarchy to the naming scheme. Ethane, ethene, ethine. Eth means 2 carbons connected together. In this case, ine means triple bond the carbons. So there's only 1 remaining H left behind. Or I show to the right of that 1,3 butadiene. Notice the similarity between the naming scheme of 1,3 butadiene and 1,3 butadiene. It's just that I'm replacing double bonds at the 1 and 3 carbons with triple bonds in the diene instead of in the diene case. Now look, I'm not going to get crazy with the nomenclature idea, but what I am going to certainly want you to recognize is the fact that carbon likes to occasionally either single, double, or triply bond to itself, and single bond to hydrogens, and when it does so, it completes an octet with no non-bonding pairs of electrons. I can extend this to pentane, hexane, octane, decane, and on it goes in the organic chemistry world. Finally, we show here some examples of carbon organic molecules with only connect carbons to carbons, and then put all remaining places with hydrogens. I show cyclic cases where the double bonds fold back upon themselves. In cyclohexane, as the name implies, the ane ending means all single bonds. Cyclo means in a ring. Hex means put 6 carbons together. So each carbon connects to 2 others and has 2 hydrogens on its remaining locations. Benzene is another specially named organic molecule that doesn't really follow conventional naming schemes, but it's unlike cyclohexane, it has 3 double bonds in the carbon-carbon-carbon-carbon ring system. So it's a 6-membered ring, but now has alternating single and double bonds between the carbons and the hydrogens. Polycyclic aromatics are just extensions of benzene, which you connect multiple benzene rings, and these become very important in the life systems. Now this is going to conclude our slides for our test number 3 that's upcoming on Thursday of next week, which would be Thursday the 26th of March. Again, I would expect you to know a little bit about these bonding ideas of carbon, but the bulk of the nomenclature and forms of these structures and things of that sort will be a topic that you will take up in organic chemistry, not so much for what we're doing here.